Ever feel like, keeping up with the latest tech, especially in fields like robotics and AI, is like trying to drink from a fire hose?
Oh, like
You're just bombarded with new terms, complex systems. And one area that really brings this home is how we get robots to actually understand and move around based on what we tell them.
vision and language navigation, or VLN.
Yep, exactly.
Yeah.
Think about it. Telling a robot, go into the kitchen, grab the apple from the counter. Seems simple for us, right?
But for a robot,
Yeah,
that's a huge puzzle.
it really is.
And that's why the research we're looking at today is, well, pretty exciting. We're doing a deep dive into a paper called Dynam3D. Dynamic Layered 3D Tokens Empower VLM for Vision and Language Navigation.
Okay.
Think of this as, our shortcut through the jargon to get to the core of a really clever approach from the National University of Singapore.
Right. And what are they tackling specifically?
They're hitting a fundamental problem. Basically, improving how robots understand their 3D environment and follow our spoken instructions to navigate. And crucially, they're focusing on robots with just a single camera.
Which is key, because that's what most practical robots actually use.
Exactly. Makes it much more relevant to real-world applications.
Okay, so our mission for this deep dive. Let's unpack Dynam 3D. We need to understand first why current systems struggle, right?
Yeah. What are the limitations?
Then how does this new method, with its dynamic layered 3D representations,
Sounds fancy, doesn't it?
it does. We'll break that down. How does that actually solve the problems? And then, what does this mean for the future? What's the real world potential?
Sounds like a plan. We want those aha moments, not just more jargon.
Definitely. So where do we start? What does a robot actually need to do for this VLN task?
Okay, well, fundamentally, you can boil it down to maybe three key things. First, obviously, it has to understand the language, the instruction itself.
Makes sense.
Second, it needs to explore, figure out where it is and where it needs to go. Localization and exploration.
Got it. And third,
Planning and action. Has to figure out the actual sequence of moves, turn, go forward to get there.
right, okay. So understanding, exploring, acting. Where do the current systems, these sort of video-based vision language models or VLMs, where do they fall short when you put them in a real 3D space?
That's really the crux of the issue the paper addresses.
Yeah.
These VLMs, they're often trained on, well, videos, flat sequences of images.
Right.
And the paper points out three main problems that arise from that. First, they just don't have a strong enough grasp of actual 3D geometry. Spatial relationships, depth, layout.
It's like seeing postcards instead of being in the room.
Kind of, yeah.
Yeah.
And that lack of 3D sense really hampers exploration. And crucially, it makes it hard for the robot to correct itself if it makes a mistake or goes off track.
Okay, that's a big one. What else?
Second, they lack what the paper calls a structured scene memory. Basically, they don't build up a persistent, organized understanding of the environment.
So if it's been in the kitchen before, it doesn't really remember the layout for next time.
Pretty much. It can't easily use prior knowledge. No real lifelong learning in that sense. And the third big challenge is dynamism.
Meaning things changing.
Exactly. People walking around, objects being moved. Because these systems rely heavily on past video frames, they struggle to adapt smoothly when the world isn't static.
That really clarifies it. I mean, the paper gives that example, go to the kitchen and take the bread out of the microwave.
Right.
For a robot to do that, it needs a 3D sense of kitchen, where a microwave usually is, and it needs to handle, I don't know, the cat running past or someone leaving a chair out.
Precisely. And the paper actually has a figure 1, that visually contrasts this. You see the video VLM approach, kind of flat processing image streams. Then you see Dynam3D, which is built around interacting with a proper 3D representation.
Okay, perfect transition. Let's talk about Dynam 3D then, the solution. It's described as a 3D language model with dynamic layered 3D representations.
Yep. It sounds like a mouthful, but the core idea is actually pretty intuitive. It's about building up this multi-level understanding of the 3D world. And crucially, keeping it constantly updated.
Low level, how does that work?
They break it down into 3 layers, or levels. Patches, instances, and zones. Think of it like zooming in and out on a map.
Okay, start with the most detailed level, patches.
Right. Patches are like the fine-grained details. They take the 2D images from the robot's camera and extract features using CLIP.
CLIP, that's the model that's really good at connecting images and language, right?
Exactly. So the features already have some language understanding baked in, which is clever. Then, using depth information, how far away things are, they project these 2D features into 3D space.
So you get like a cloud of points in 3D representing surfaces and textures.
Pretty much a dense 3D feature map. That's your base layer.
Okay, so fine details covered. How do we get from points to actual objects? That must be instances.
You got it. Instances are about identifying individual objects. They use another model called FastSAM, which, as the name suggests, is quick to find objects in the 2D image.
Like drawing boxes around things.
Sort of. It generates masks, outlines. Then it grabs all those 3D patch features that fall within an object's mask and groups them together.
Ah, so now you have a collection of 3D points that represents, say, a chair or a table.
Exactly. And it also tries to keep track, saying, okay, this group of features is the same chair I saw a moment ago, making the object understanding consistent over time. The goal is aligning these 3D objects with language understanding.
Okay, points to objects. What about the highest level zones?
Zones give you the big picture. They represent larger spatial areas like kitchen, living room, hallway,
How does it figure those out?
by basically grouping together the features of the 3D instances that tend to appear in certain areas. So if it sees a sofa instance, a TV instance, a coffee table instance, all close together in 3D space, it might group them into a living room zone.
Got it. So it's building this layered understanding, detailed points, distinct objects, and then broader areas or rooms.
Precisely. It gives the robot a much richer, more structured understanding of the environment's layout.
And the dynamic part, how does it keep all this current?
Right, that's key. It uses a technique called frustum culling. Imagine the robot's cone of vision.
Okay.
As it moves, any old patch features that are now outside its view or haven't been seen for a bit get removed.
Yeah.
Keeps the memory manageable.
Cleans out the old stuff.
Yep. And simultaneously, anything new it sees generates new patch features, which then get processed up into instances and potentially update the zones.
So it's constantly pruning and adding information.
Exactly. That's how it adapts to changes and maintains this lifelong up-to-date map is where it's been. There's a diagram, figure 3, in the paper that shows this constant update loop pretty clearly.
Okay, this system sounds quite sophisticated. What would you say are the really core innovations here? What makes Dynam3D stand out?
Well, the paper highlights 3 main things.
Huh?
First, as we've been discussing, it's the dynamic layered 3D representation itself. This whole process of online encoding, the real-time updates across patches, instances, zones, that's fundamental.
It's moving beyond just processing video frames sequentially.
Totally. It's about building a truly dynamic, multifaceted 3D understanding. It allows the robot to, comprehend space, much more like we do, not just react to pixels.
That makes a lot of sense. Okay, what's the second big innovation?
The second is how they integrate this with the language model, the 3D vision language model integration. They feed both the detailed 3D patch features, captured panoramically, and the higher-level 3D instance and zone features into the VLM.
So the language model gets this really rich 3D context, not just flat images.
Exactly. And the model they use, the Laval 3 Mini, is actually quite efficient for its power, 3.8 billion parameters. Integrating these different levels of 3D data into a capable VLM is a significant step.
And this combined 3D VLM, how does it actually decide where the robot should go based on the instruction?
So it takes the language instruction, like go to the sofa, plus the history of actions the robot has already taken.
Okay.
And based on the current 3D understanding from the patches, instances, and zones, it directly predicts the next action. Simple things like turn left 30 degrees, move forward half a meter, or stop.
So it's outputting navigation commands directly.
Yes. And they also mention they specifically encode the relative spatial positions of all these 3D tokens, the patches, instances, zones, relative to the robot itself. That helps ground the language in the spatial reality. Figure 2 in the paper lays out this whole architecture.
Okay, the architecture sounds impressive, building this dynamic 3D world model and linking it to language. But the million-dollar question, does it actually work better? What do the results show?
Ah, yes, the results.
No,
This is where it gets pretty compelling. They tested Dynam3D on several standard VLN benchmarks, R2RCE, Reverie CE, NABRAG CE, and crucially, under the monocular setting, just one camera. And it achieved state-of-the-art results. Significant improvements in success rates, how often the robot actually reached the target, compared to previous top methods like G3D, LF, and Uninavid.
Uninavid, wasn't that a much larger model?
It was. That's a key point. Uninavid has, I think, 7 billion parameters. Dynam3D is getting better results with a much smaller, more efficient 3.8 billion parameter model.
Wow, okay. Better and more efficient. That's a big deal for actually using this stuff.
Absolutely. Tables 1 and 2 in the paper lay out the specific numbers if you want to dig into those comparisons.
That's impressive. Did they test those specific ideas about memory, like letting it explore first or remembering things across tasks?
They did. They ran experiments on what they called pre-exploration, where the robot gets to map the area beforehand,
Okay.
and also lifelong memory, where it does multiple navigation tasks in the same environment and retains information
And did that help?
massively. In both scenarios, the success rates jumped significantly. Table 3 shows this, like, compared to another approach called NAVID, Dynam3D with pre-exploration and lifelong memory boosted the success rate by over 20 percentage points on some tasks.
Yeah, over 20%. That's huge.
It really is. It strongly backs up the value of building and maintaining this persistent 3D memory. It's not just about reacting, it's about knowing the environment.
That feels like a real aha moment, doesn't it? Memory and pre-mapping actually make a massive difference, but simulations are one thing. Did they try it on a real robot?
Yes, absolutely critical step. They used a Hello Robot Stretch 3
Okay.
and tested it in real-world settings, both static environments and, more challengingly, dynamic ones.
Dynamic like.
Like, in one test, they actually moved the target object while the robot was on its way.
Oh, wow, that's tough. How did it cope?
It performed really well.
Mm.
The results, shown in tables 4 and 5, and there's a figure 4 too, demonstrate it's much more robust and achieves higher success rates in these messy real-world scenarios compared to other methods.
And it can do all this processing fast enough, in real time.
They looked at that too. And yes, they report that the system supports real-time updates and action prediction. That's crucial for practical robotics.
Okay, and did they do those studies where they, like, turn off parts of the system to see what matters most? Ablation studies?
Yep, they did. Table 6 has the details, and it confirmed their design choices.
Mm-hmm.
For example, taking out the 3D instance or zone representations, performance dropped quite a bit.
So those higher levels of understanding are really important.
Very important, especially for exploring larger areas and navigating effectively. They also showed their learning technique, subspace contrastive learning, was effective in aligning the visual and language parts. It really validates the whole layered approach.
So let's bring this back home for you, the listener, trying to keep up. It sounds like Dynam3D is a really significant step. It helps robots understand and move through our complex, changing world based on just talking to them.
I think that's fair to say. It really pushes towards robots that are more intuitive, more capable partners in everyday life, whether it's helping at home or in other settings.
So to sum up the key takeaways,
It's really about that dynamic, layered 3D representation, patches, instances, zones, combined with a 3D-aware language model. That combination tackles major limitations of older systems.
yeah, right. The structure itself and the constant updating, that seems to be the magic sauce.
That's what leads to the state-of-the-art performance, the efficiency, and importantly, the robustness in real-world tests.
No system is perfect. Did the researchers point out any current limitations?
They did. They're quite upfront about it. For instance, right now, Dynam3D predicts actions, but it doesn't explicitly say the target is at these exact coordinates.
Ah, okay. So maybe less suited for very precise manipulation tasks just yet.
Potentially. They also note it can't currently do things like answer questions about the environment, what color is the sofa, or handle updates to the task mid-navigation. Actually go to the fridge instead.
Okay, so still room for growth.
Definitely. But they frame these as exciting avenues for future work, building on the solid foundation Dynam3D provides. Not really deal breakers, more like next steps.
That makes sense. Progress, not perfection, right?
Hmm.
So, as we wrap up this deep dive, here's something for you to chew on. Thinking about Dynam3D's ability to build and update this rich 3D understanding,
Hmm.
what new kinds of robots does this make you imagine?
Yeah, beyond just go fetch, what could a robot that truly understands its 3D space and language do? Assistive roles, exploration.
Could be fascinating, something to ponder.
And if you do want to get into the nitty-gritty, the paper mentions the code, and more details are available on GitHub.
Great. Well, thanks for joining us on this deep dive into Dynam3D. Really interesting stuff.
My pleasure. Always exciting to see the field moving forward.
Until next time, keep exploring.